Okay, in this video, I'm going to go over two examples of exponential modeling. So this first problem, we have a town with 1,500 people infected with COVID, and each day a person has a 1 in 9 chance of spreading COVID to someone else. We're also going to assume that the average infection lasts 11 days. So this problem prompts us to create a discrete model and a continuous model to model the spread of the disease. Other problems that are like this might then prompt you to graph these models or compute how much someone is infected or how many people are infected after a certain period of time passes. We're just going to skip that for right now and just focus on building the model. All right, so we want to pick out a few key pieces of information. So the first piece that's relevant to us is that we have 1,500 people infected to start with. The next piece is that there's a 1 in 9 chance of spreading COVID. And the third piece that's important is that there's 11 days that they're infected. All right, so we'll first work with this 11 days. In our COVID models, we want everything to be a rate. And so since we have that the average infection lasts 11 days, we expect that 1 in 11 recover each day. And that sort of makes sense because then if you had a population on day 0, then after 11 days, you would have that entire population has recovered because 1/11 would have recovered, another 11th would have recovered, and so on. Okay, so now we just set up our COVID model. We'll start with the discrete one. And this is really just plug and chug at this point. We have f of n, where n is days elapsed. We want to multiply by how many people are currently infected. And then we do our exponential rate, which for the discrete model is always 1 plus the rate that are becoming infected, so that's 1/9, minus the rate that are healing, 1/11, and then raised to the n. And so overall that equals 1,500, and then we can start to simplify. So we'll make a common denominator. It's 99 over 99 plus 11 over 99 minus 9 over 99 to the n, which equals 1,500 to the, that'll be 101 over 99 to the n. And so that's our discrete model. It's slightly greater than 1. So that means it is going to exponentially grow. So as time passes, more and more people become infected, eventually until everyone's infected in this model. Because this is greater than 1, and as we raise something greater than 1 to a power, it goes off to infinity. But it's close to 1, so that growth will be slow. All right, let's try another example, or move to the continuous model, sorry. For the continuous model, now we usually use the variable t. N is usually reserved for integers. T is going to let us plug in anytime. Obviously for n, we could plug in anytime we wanted, but for t, it's just a signal to whoever's looking at your model that you're working with a continuous time model that you can plug in anything you want. So for the continuous time model, we plug in the same, we start with the same stuff. It's the same recipe, just a little bit different. We now have 1,500, and instead of having this 1 plus 1/9 minus 1/11, we instead just get an e. And then we have to raise our e to the rates that we have. So we have our rate n, which is 1/9, so people becoming infected, minus 1/11. That's our rate of people healing. And then we just multiply by time. And we can start to simplify, so that's 1,500 e to the 11 over 99 minus 9 over 99 times t, which is 1,500 e to the 2 over 99 times t. So again, in this model, because this is positive, we're going to start to grow. Yeah, and that's all there is to it for these discrete and continuous models. It's really just plugging in the numbers properly. If we wanted to know, say, how many people are infected on the 99th day, then we would just do f of 99 and just evaluate the function. That's 1,500 e to the 2 over 99 times 99, or just 1,500 e squared. And e squared is about 8, not exactly 8, but about 8, so this would be about 1,500 times 8, which is about 12,000 people are infected. All right, so for the next one, I have a slightly more complicated exponential model that we can look at. All right, so we have, in this case, we have a city with 1,700 people infected with COVID. And the 1,700 is different than the 1,500, but it shouldn't actually change anything in our models. We should just, wherever we see a 1,500, just replace it with the 1,700. So we have 1,700 people infected and spreading at a rate of 0.11 a day. And recovery takes 20 days. After 30 days, the mayor of the city notices that there's a spike in cases and institutes a shutdown that ends up reducing the spread by 0.1. So that's 10%. Create a continuous exponential model that models infection over time. So this one, we're going to end up needing a piecewise function to account for what happens before 30 days and then after 30 days. So that makes this model a little bit interesting. So before 30 days, it's pretty easy. It's the same thing that we just did. So before 30 days, we have f of t equals 1,700. So that's our rate that we initially had infected. E. Then we have let's see, so we have 1,700 E. We need our rate of people becoming infected. So that's 0.11. And now we need our rate of people healing. If it takes 20 days to heal, that means that it takes 1 in 20 heal a day. And so that's 0.05 heal a day. So we have 111 minus 0.05 times t. So that's 1,700 e to the 0.06 t. So that's our model for the first 30 days. Super straightforward. All right, so after 30 days, we have a change in our model. So after 30 days, our model now becomes f of t equals some number is going to go there. And then we also have a rate that we're changing. So let's get this rate first. We have e. Now we have 0.06 t before. So our effective rate was 0.06, but now we're subtracting 0.1 from it to get us minus 0.04. And then it turns out that we need t minus 30. Because now it's like we're resetting at a new time 1. So if we're decreasing at this rate, if we plug in day 31, then we've only been decreasing at this rate for effectively 1 day. So this minus 30 adjusts for that. And then our number out in front is just how much time, or is the new infected population on day 30. So we just need to know how many people are infected on day 30. So that involves evaluating f of 30 from above, which is 1700 e to the 0.06 times 30, which I used a calculator to evaluate and found that it's approximately 10,284. All right, so now we can create our model where we have f of t equals, we get this piecewise function where on the top it's 1700 e to the 0.06 t for t less than or equal to 30. And then 10,284 e to the minus 0.04 t minus 30 for t greater than 30. And we can draw a graph of this as well. So this is just going to be graphing a piecewise function. Label a couple important points. So that's 1700. Maybe up here we'll put 10,284. And we'll put 30 days right there. So at day 0, we start here at 1700. At day 30, we better be up here at about 10,000 infected. So our curve's going to look something like this, and it's shooting up. And then the shutdown is put in place, and then cases start to fall. So the graph will look something like that. All right, so again, let's just review how we got this model. I think the top part is straightforward. The 1700 e to the 0.06 t, that's just our standard COVID model. The interesting part comes where after 30 days, we have a new restriction put in place. And so the key things to take away from there are we have to adjust this t. So that way when we plug in f of 30, it's like adjusted for this t. And then also the new infected population. So essentially the way this is working is if we didn't have this minus 30, then this would be a perfectly fine model if our model was starting at t equals 0 for this case, but since it's starting at t equals 30, we need that minus 30 there. All right, well, ponder over how this model works. And I hope these 2 examples were useful. All right, see ya.